Hi Rockridge, this is Mrs. Berger, and today we'll be discussing function inverses. This is the last of the new material for Unit 3. One main thing that you'll need to remember for inverses is that an inverse of any relation or function is when we swap x and y. Okay, that's the basic crux of everything we'll be doing in this lesson. So if you have a relation like this set of points right here, if you swap x and y values and turn the y value into an x value and an x value into a y value, you will have the inverse of that relation. Notice that when we have -3 in the x value, the negative sign comes with the 3 when we swap it with x. So let's just demonstrate what it would look like to have the original relation and the inverse graphed on the same coordinate plane. So the original one we'll do in purple. So 1, 1, 2, 3, 4. -3, 2, and 7, -9. Maybe somewhere down here. That's the original relation. And then if we were to do the inverse of that relation, we would swap x and y, and we would graph 4, 1, 2, -3, and -9, 7. So the orange is the inverse, the purple is the original relation. Okay, so swapping x and y, that's what an inverse is. Let's graduate a little bit to a function now. If we need to graph the function in purple and the inverse in orange, let's watch how that happens. Now, the original function is f of x equals 2x plus 1. This is a line of the form y equals mx plus b. We know how to graph these. We find the y-intercept, and we count from there on a slope of 2 over 1, right there. And then we connect those points. And since nobody told us this line has a limited domain, we assume that it goes off in both directions. So that's our original f of x. This is f of x. Now, to graph the inverse, I can simply choose to collect points and swap the x and y values. So if the original point here is -1, -1, the new point will also be -1, -1, because if you swap, it's the same point. If the original point is 0, 1, the new point will be 1, 0. If the original point was 1, 3, the new point will be 3, 1. Let's see, 1, 2, yes. 1, 2, 3, 1. There we go. Sorry about that. So my new line looks like this. That is my inverse. And let's introduce some notation here to show that this is the inverse of f. This is how we indicate that is the inverse of the f function, f to the -1 of x. Okay, that's just notation. Now, an interesting thing, especially if you are a graphically minded or artistically minded person, is that if you are visually checking to see if you have done the inverse correctly, you can look at it and say, all right, have I taken my original function and reflected it across the line y equals x? Let me show you what that means. The line y equals x looks like this, right? Goes through 0, has a slope of 1 over 1. That's y equals x. Have I taken the purple original function and reflected that or folded it across the pink line, y equals x? If you say yes, visually, that's a visual check to say I have done the inverse correctly. I've taken that purple line and folded it across the pink line, y equals x, and I've created the orange line, and yes, that's exactly what happened there. I rotated it or reflected it across there. So that's a visual check you can always do. If on a quiz or a test you think maybe your algebra was wrong, that's a little visual test you can say, does it look like I've reflected it across the line y equals x? This is always your checkpoint. Another interesting fact about these functions is the horizontal line test. Remember the vertical line test? Let's just make a little fake function here. The vertical line test says if you can find any vertical line that cuts the function more than once, the graph more than once, it's not a function. So this original pink function is a function because it passes the vertical line test. The horizontal line test, however, says if you can find a horizontal line that cuts the graph more than once, the inverse is not a function. If a horizontal line cuts the original function more than once, the inverse is not a function. Okay? So if you need to pause and think about that, you're more than welcome, but that's a little quick test. All right, now let's graduate a little bit to inverse functions. And again, inverse functions is when we swap x and y. Now instead of having a set of points or a relation to find the inverse of, we have a function. Our first function, number 13, is y equals 2x minus 4. These steps, A, B, and C, are the steps we'll walk through to find the inverse. The first thing we need to do is swap x and y. Always switch the variables, swap x and y. And what I mean by that is, if you see a y in the original, replace it with an x. If you see an x in the original, replace it with a y. Okay? That's step A. Step B is to solve for y, or get y by itself. Basically, I tell my students, get this to a point where you could possibly put it in your graphing calculator in y equals form so that you can visually look and see if that new function is the inverse, if it's been reflected. So add 4 to both sides and divide by 2. And now you have y by itself. You've solved for y. Our last step is to put the correct notation. Remember what I said about how to notate the inverse of a function? The inverse of y, that's what that means, the inverse of y to the negative 1, the inverse of y is x plus 4 over 2. So that little last step is just a cleanup notation thing. Let's try it again with number 14. Now the interesting thing about 14 is it's called, we named it f of x instead of y. No problem, we will just need to do ourselves a little favor though. Let's call this, just for temporary sake, y. Because when we swap x and y, it's just helpful to think of this in the y format instead of the function format. We'll go back and fix the notation in step C. But for right now, for swapping purposes, let's call this a y function, just temporarily. So let's do step A, swap x and y. And then we'll solve for y. Subtract 3 from both sides. Multiply both sides by 2. We'll clean this up a little bit. Y is now by itself. We've solved for y. Our last step is to put this in the correct notation. Now if the original function was named f of x, our correct notation for the inverse of f is f to the negative 1 of x is 2x minus 6. Remember, that last little step is just a cleanup of notation. So the inverse of that function f is 2x minus 6. If that went any too fast for you, please pause the video and try that for yourselves. Let's look at 15. 15 is called h of x. H of x is x squared. Let's, for temporary sake and just for simplicity's sake, call this y equals x squared instead, just for a moment. Our first step is to swap x and y. The next step is to get y by itself. Remember from our previous unit, in order to get y by itself, to get that power of 2, we counteract that with a square root. And remember when we take an even root, remember from earlier units, when we take an even root, we have to have plus minus. So that's step B. We have isolated y. Now we need to go back into the original format of the function. This was called h of x, so we're going to call the inverse h to the negative 1 of x. That is, the inverse of h is plus and minus square root of x. If you'd like to try 16 on your own before I go through it, please pause the video and try it on your own. If you're not pausing, or if you've finished it, let's go ahead and look at it. We're going to replace g of x with a y to make it a little simpler on ourselves. It's just a temporary step. We're going to swap x and y. Notice coefficients do not go with the variables, nor do powers. Make sure that you only pick up the x and only pick up the y. Don't pick up anything that's glued to the front of it or that is the exponent on it. Now we'll solve for y. Remember from previous units how to do this. To counteract that square root, we're going to bring it to a power of 2. So y plus 2 equals x squared. Y equals x squared minus 2. Our last step is to get this in the proper notation. The original name of our function was g of x, so the inverse of g is x squared minus 2. Let's take a look at a couple more. Once again on 17 we have a relation. Don't get tricked by this. This is the simple one. We love these, right? Just swap the variables, bring the signs with them. Hopefully that was pretty good. And then on the last one, if you need to pause the video and try it on your own, please do so. Let's take a look at how the last one goes. We're going to call this y temporarily to make this easier on ourselves. Then we're going to swap. Then we're going to solve. And remember what we do to solve this. Cube root, cube root. So y equals the cube root of x minus 2. Let's get this back in the correct notation. The inverse of h, since this was originally called h, the inverse of h is the cube root of x minus 2. If any of that went too fast, please pause the video, rewind, replay it, try things on your own. There will be time at the end for group practice as well. Alright, the last thing we need to know for this unit is how to verify something is an inverse of another function. And we have this little proof here. If somebody throws two functions at you, f and g, and says, hey, are these inverses of each other? The way you can prove they're inverses of each other is to do a composition. If f of g of x equals x, and g of f of x equals x, both, then you have two functions that are inverses of one another. If either one of those does not simplify down to x, you do not have functions that are inverses of each other. You will be asked to perform this. You'll be given this proof. So let's see how this works on question number 6. If someone says determine if they're inverses of each other, or verify if these are inverses of each other, or prove that these are inverses of each other, you'll first ask, all right, well, what's f of g of x? This is composition from an earlier lesson, so we should have practice on this. For the f function, my input goes in the parentheses there. And in this case, I am inputting g in there. If I was to simplify this, I will distribute the 1/2. And x minus 2 plus 2 can be simplified down to x. So I'm halfway there. I have proven that f of g of x does in fact equal x. If I can also prove that g of f of x equals x, then I will have proven that this f and g are inverses of each other. So let's see if that's the case. For the g function, I put my input in those parentheses, and in this case my input is the f function. I'll distribute the 2, and when I combine those terms, I once again have x. So yes, they are inverses of each other. F and g are inverses of each other. Some of you might ask, well, can't I just find the inverse of f, and if it's the same thing as g, then I've proven it? Yes, that's absolutely a check, but when I want you to verify an inverse on a quiz or test, I specifically am looking for your ability to find the compositions. You need to prove you're able to do the compositions. Let's check 7. My first step on 7 will be f of g of x. f of g of x means, f of g of x means I put my input into the parentheses, and my input in this case is negative 3x plus 9. I'll distribute the 3, and I'll combine like terms. F of g of x can only be simplified down to negative 9x plus 18. That is clearly not x. If f of g of x does not equal x, there's really no reason to ever go to the next step of g of f of x. Because if one doesn't equal x, then they're definitely not inverses. Okay? Now, you are going to try the group practice on your own. Try these problems on your own and check your work against the key. If you have any questions about this, get with your teacher before the quiz and the test. Thanks.